Welcome to our tutorial on inverse Laplace transforms. In this video, we'll explore how to convert functions from the s-domain back to the time domain, step by step. First, let's understand what the inverse Laplace transform actually is. If f of s is the Laplace transform of some function f of t, then the inverse Laplace transform, denoted by L inverse of f of s, gives us back the original function f of t. Formally, we can define the inverse Laplace transform using what's called the Bromwich integral. But don't worry. In practice, we rarely need to use this complex integral directly. Instead, we use tables of known transform pairs and algebraic techniques, like partial fraction expansion. Let's look at some common transform pairs that we'll frequently use. First, the inverse Laplace transform of 1 over s is 1. Next, the inverse Laplace transform of 1 over s minus I is e raised to the power at, for omega over s squared plus omega squared. The inverse is sine of omega t. Similarly, for s over s squared plus omega squared, the inverse is cosine of omega t. And lastly, for n factorial over s to the power n plus 1, the inverse is t to the power n. These transform pairs form the foundation for solving more complex inverse Laplace transforms. When we encounter a complicated function f of s, our strategy will be to break it down into these simpler forms whose inverses we already know. Now, let's discuss the step-by-step method for finding inverse Laplace transforms using partial fraction expansion. Step 1. Factor the denominator of f of s, assuming it's a rational function. Step 2. Decompose f of s into partial fractions. This gives us a sum of simpler terms. Step 3. Solve for the constants in your partial fraction expansion. Step 4. Apply the known inverse transforms to each term individually. The key insight is that the inverse Laplace transform of a sum equals the sum of the inverse transforms of each term. This property makes our approach very powerful. Let's work through our first example to see this method in action. We want to find the inverse Laplace transform of the function f of s equals 3s plus 5 divided by s squared minus 2s minus 3. Step 1. First, we factor the denominator. S squared minus 2s minus 3 equals s minus 3 times s plus 1. Step 2. Now we write the partial fraction expansion. We get a over s minus 3 plus b over s plus 1. Step 3. To find the constants a and b, we multiply both sides by the common denominator. This gives us 3s plus 5 equals a times s plus 1 plus b times s minus 3. To find a, we substitute s equals 3. This gives us 3 times 3 plus 5 equals 14 equals a times 4. So a equals 3.5. To find b, we substitute s equals negative 1. This gives us 3 times negative 1 plus 5 equals 2 equals b times negative 4, so b equals negative 0.5. Step 4. Now we can rewrite our function as 3.5 over s minus 3 minus 0.5 over s plus 1. The inverse of 3.5 over s minus 3 is 3.5 times e to the power 3t, and the inverse of negative 0.5 over s plus 1 is negative 0.5 times e to the power negative t. So our final answer is f of t equals 3.5 e to the power 3t minus 0.5 e to the power negative t. Let's move on to a second example that involves a different type of fraction. We want to find the inverse Laplace transform of f of s equals s plus 2 divided by s squared plus 4. Looking at the denominator, we see that s squared plus 4 equals s squared plus 2 squared, which is an irreducible quadratic. Unlike our previous example, we can't factor this further. However, we can split the numerator to match our known transform pairs. We get s over s squared plus 4 plus 2 over s squared plus 4. Now we can use our transform pairs. The inverse of s over s squared plus 4 is cosine of 2t, since omega equals 2 in this case. And the inverse of 2 over s squared plus 4 is sine of 2t, again with omega equals 2. Note that this is actually 2 times sine of 2t because we have a factor of 2 in the numerator. So our final answer is f of t equals cosine of 2t plus sine of 2t. Let's visualize the result of our second example to better understand what we've found. The blue curve represents cosine of 2t, and the green curve represents sine of 2t. When we add these functions together, we get the red curve, which is our final answer, cosine of 2t plus sine of 2t. An interesting property of this sum is that it can be rewritten as the single function root 2 times sine of 2t plus pi over 4, which has an amplitude of root 2 and a phase shift. This is why the red curve has a larger amplitude than either of the component functions. Before we conclude, let's go over some important tips and tricks for finding inverse Laplace transforms. First, always simplify algebraically before attempting to find the inverse transform. Factor the denominator, combine like terms, and get the expression into a standard form. Second, match each term to a standard Laplace transform pair. Keep a table of common pairs handy as you work through problems. For repeated roots of the form s minus a to the power n, use the formula. The inverse Laplace transform of 1 over s minus a to the power n equals t to the power n minus 1 over n minus 1, factorial times e to the power at. And for irreducible quadratics, use the form 8s plus b over s squared plus omega squared, which can be split into terms involving sine and cosine functions. With practice, you'll become more adept at recognizing patterns and quickly decomposing functions into simpler forms whose inverse transforms you know. Start with simple examples and gradually work your way up to more complex rational functions. In summary, the inverse Laplace transform allows us to convert functions from the S-domain back to the time domain. We can find inverse transforms using 1. Tables of known transform pairs. 2. Partial fraction expansion for rational functions. 3. Algebraic manipulations to match standard forms. The key is to break complex expressions into simpler pieces whose inverse transforms we already know. With these tools, you're now equipped to tackle a wide range of inverse Laplace transform problems. Thank you for watching.